All right, thank you very much. Hello, everybody.
Hello.
Good morning, or good afternoon, or good evening. Um, and thank you to the organizers for inviting me to give this talk. So I'm going to try and give a quick overview of the status of the Hubble tension, which is a very exciting open problem in cosmology. Um, I want to start by just trying to summarize in one admittedly quite long sentence, what is the Hubble tension? So I've had a shot at this in the sentences at the bottom of the slide. So the Hubble tension is the disagreement between H naught values inferred within the standard lambda CDM cosmological model from observations of the early universe and more direct low redshift measurements. So on the one side, we have observations including the cosmic microwave background, baryon acoustic oscillations, and I'll talk more about these measurements. And they prefer a low value of H naught or predict a low value of H naught. And on the other side, the more direct measurements, and I'll focus on the cosmic distance ladder, that more or less use Hubble's law with some modifications, but more or less are tracing out the relationship between distance and cosmological recession velocity or redshift to directly measure H naught. So I'll go through each of these observations, and then in the second part of the talk, I'll turn to the question of how modifications to the cosmological model might be made to reconcile this disagreement. So I'm going to start with a few slides from Adam Rees, who is the PI of the SHOES program. The SHOES program provides the most precise distance ladder constraints to date. SHOES stands for supernovae H naught for the dark energy equation of state. So how do we map out that redshift distance relation precisely enough to get an H naught constraint of roughly percent uncertainty? Well, it's not easy. So our best astrophysical distance indicators out to cosmological distances are type 1a supernovae. So these are extremely luminous. And because the white dwarf progenitors have roughly a constant mass at the time of the explosion, we end up with a roughly constant peak luminosity of the supernova. So if you knew what that peak luminosity was, observations of a single supernova event could give you a distance good to about 5%. So you can imagine that if you had a large enough sample of supernovae, you could beat down the statistical uncertainty on this and get extremely precise distances. The problem is we don't know theoretically or a priori what that peak luminosity actually is. So the challenge in the distance ladder is to calibrate the peak luminosity of the supernovae. And essentially we need an absolute distance to a supernova or a galaxy where a supernova has gone off in order to then make use of the supernovae at higher distances out at a higher redshift. And that's where the second distance indicator comes in. So the SHOES team use Cepheid variable stars. They're extremely luminous, so 100,000 times the luminosity of the sun. And that's important because we can see them in nearby galaxies out to a distance of something like 30 megaparsecs. So we can see the Cepheids in galaxies where supernovae have gone off. And what that means is that we can sort of build a ladder where if we know the distance to Cepheids, and if Cepheids give us then the distance to the galaxies of the supernovae, then we can reconstruct the distance redshift relation and constrain H naught. So the property of Cepheids, and this is an empirical relation, the property of Cepheids that lets us do this is a tight period luminosity relation. So that these pulsations with periods of order days in some cases, or many tens or certainly many tens of days in the long period cases. And so if we can study enough Cepheids, map out this period luminosity relation, then we can essentially build up this distance ladder. So this slide tries to illustrate this in a cartoon form here on the left. So we start at the bottom. So Cepheids are found in the Milky Way, which is great because we can measure absolute distances using, for example, parallax. So just the annual apparent movement of a star against the background of more distant stars. So that gives us an absolute distance to get started. And then we can use the period luminosity relation for the Cepheids to measure distances out to galaxies containing Cepheids that are further away, far enough away that we can come up with a sample of such galaxies where a supernova has gone off. And so this is like the step where the supernovae get calibrated. And then we use the supernovae that are out in the Hubble flow out to redshift around 0.1. And that's what finally gives H naught. So it's a little complicated, and the naught in H naught, we're not really measuring at redshift naught because there's no volume at redshift naught, right? But this is as good as we can do. It's a technique that's been refined over many decades, critically due to the Hubble Space Telescope. And I want to emphasize here that this is an empirical and model-free or virtually model-free measurement. So it's virtually independent of assumptions about the cosmological model. So that's what this little cartoon nutrition facts is supposed to be indicating. It's not really sensitive to the details of what the universe is made of. I'm not sure why the serving size is one potato, but yeah. The point here is that this is a very nice way to measure a cosmological parameter of fundamental importance without having to go through a model. Okay, so the state-of-the-art measurement from the distance ladder brings together a whole host of observations. I'll try and talk you through what this plot is showing. So here we are at the first rung with parallax of Cepheids in the Milky Way, like I mentioned. There's actually a few different ways to measure absolute distances to Cepheids. I'll come back to that in a minute. So these are all very nearby galaxies where we can come up with these absolute independent distances. Then this middle rung are these 19 galaxies where there's a supernovae and a population of Cepheids. So we get the distance of the galaxy from the Cepheid period luminosity relations. And then finally, there's a select sample of about 300 supernovae that are then used to map out the distance redshift relation thanks to the calibration from these guys. So you add all of that together and you get to an H naught of 73.2 plus or minus 1.3, where this error bar and all the error bars I'm showing include all known sources of systematic uncertainty. And this is the state of the art for the distance ladder. And it's in 4 to 6 sigma tension, depending on exactly how you count the data sets, from the CMB Lambda CDM prediction that I'll get to in a few minutes. Okay, and I wanted to just show a couple more slides about the robustness of this measurement. So because this is an empirical measurement, obviously there's interesting underlying physics in the Cepheids and in the supernovae, but we don't use a fundamental physics prediction to measure H naught here. We're using phenomenological or empirical relations. And so those relations have to be constantly tested and validated as we get more data to check that they still work, essentially. And one of the big limitations in the ladder historically was actually that first rung, so measuring absolute distances out to the Cepheids. And a big recent development has come from the Gaia mission, which has given us a whole bunch of new parallaxes within the Milky Way, and also various other techniques. You can see the dates here, the last couple of years, have also given more precise and more robust absolute distance measurements. So now you don't need to rely on any single one of these, what Adam calls anchors, to get you started on the distance ladder. So there's a total of 7 here, which is across several independent techniques and independent data sets. And if you use them one at a time, you can get through to a final central value of H naught, which you see in this final column here. And there's certainly some variation because a large part of the statistical uncertainty in the measurement does come from that first rung. But you can see that they're all high of 72. Okay, none of these are coming down to the low values from the early universe side. And equally importantly, the distance ladder has been reanalyzed by many independent groups, as well as within the SHOES team. So I just put up cutouts from various archive posts for a range of the analyses in the past few years, digging in at the level of the raw Hubble images, refitting parts of the Cepheid ladder, making different assumptions about the supernovae, different samples of the supernovae. And this is extremely valuable, of course, and it has helped improve the SHOES analysis. And the overall conclusion from this is that so far, the SHOES distance ladder has held up. There's not been a result that's come out that says, oh no, this is all wrong so far. As I said, it's of course crucial to keep testing these empirical relations. So partly because of the Hubble tension, there's been a huge observational effort to independently measure H naught, what you might call locally or directly. I'm not going to go through the whole of this figure, but it's a figure from a recent review. So this red bar here is the Planck lambda CDM constraint, and then there's different categories of direct measurements. So I've just been talking about the Cepheid supernova ladder and this data point up at the top. There's various other ways one can measure H naught that are partially or fully independent of this ladder. And some of these techniques go back decades. Some of them are being developed very recently, or even with sort of prospects for the future, including gravitational wave constraints that were mentioned in the previous talk. So I guess what I want you to take away from this is that generally speaking, these other methods are giving us high values, high relative to Planck. There are some of these measurements that are consistent with Planck, though. They're not all in tension. And this is an extremely active area of research. And so over the next months to years timescale, there's going to be a lot of improvement on the lower part of this plot. So we'll have many independent checks on the distance ladder value. Okay, so if I covered things a little too quickly there, I wanted to just stop for a second and summarize the late time observations. So the most precise constraints are from this empirical distance ladder I've been talking about. It uses the period luminosity relation from Cepheids and the consistent peak luminosity from supernovae. There have been many reanalyses and consistency tests, both within the SHOES team and independently. In my view, in light of these tests, there's currently no compelling reason to throw out the SHOES results. And there's this enormous observational push for other measurements, which will be providing new results, some with precision comparable to the SHOES constraint on month to year timescales. All right, let's turn our attention to the early universe. So starting with the cosmic microwave background, I'm going to talk about the Planck mission in particular. So Planck provides the most precise CMB cosmology results. The bottom line from the Planck team is this: we find no compelling evidence for extensions to the base lambda CDM model. So the story from Planck is that base lambda CDM works great. And very briefly, the Planck satellite measured the fluctuations in the CMB temperature across the full sky. The statistical properties are encoded in the temperature power spectrum shown here, which is essentially the variance in the temperature as a function of separation of pairs of pixels in the map. And from the power spectrum, we can then fit cosmological models and obtain very precise constraints on the composition and properties of the universe. So that's how you get these pie charts showing the fraction of this is showing present day energy density in dark matter, ordinary baryonic matter, and dark energy. So the CMB is sourced at recombination. Almost all the information in the CMB map is from a time when the universe was a few 100,000 years old. So long before any nonlinear structure formation, before any formation of galaxies. And it's only within the lambda CDM model or models, sort of simple models similar to it, that we can make precise extrapolations or predictions for what the universe should look like today based on the CMB. So it bears emphasizing that the CMB H0 really is very model dependent. And a final point I wanted to make here is that even though the temperature power spectrum historically has been the powerful statistic that's been used for cosmology, there's actually a partially independent check also from the CMB using linear polarization. So here is the H0 constraint from all of the Planck data put together. And the constraint just from cross-correlating the temperature and the E mode, that's the curl-free components of linear polarization. So just that spectrum, not any of these data points, gives an H0 value of this with, again, a small error bar and a preference for values less than 70. So this is already a useful cross-check. Okay. Another data set I want to highlight here are measurements of baryon acoustic oscillations that are intimately connected to the physics of the CMB. So the spacing of the peaks in the power spectrum is essentially this scale that we call the BAO scale. And it's how far sound waves propagate in the plasma before recombination, so before baryons and the photons decouple. So the CMB tells us, if you like, the photons side of the story. but the electrons and protons and to some extent the dark matter are coupled into or sensitive to this competition between the gravity and the pressure waves within the early universe. And that same scale imprinted in the CMB as the peak spacing, this sound horizon, is also imprinted in the large-scale structure of the universe. So even though there were no galaxies and no structure formed at the time of the CMB, if we study the distribution of galaxies in the much later universe, we can still see an imprint of this same BAO scale that was put there back at recombination. And so this is a very powerful consistency test that we understand what the CMB is telling us. And so this key distance is this sound horizon called R subscript D, and it's this integral across the early universe for sound speed divided by the Hubble rate. And one thing that's really important about this is that the BAO scale is actually large enough to be more or less unchanged by subsequent nonlinear growth and evolution. So if we have a very large volume of galaxies or other traces of large-scale structure, we can measure this scale in the late-time universe and compare what we measure in the CMB. And as I said, this is a powerful check that we understand how the universe has expanded. Okay, and I wanted to name drop one very important experiment, the Baryon Oscillation Spectroscopic Survey, or BOSS, which has given us the tightest BAO constraints to date. So this is a survey of 1.4 million massive galaxies over about a quarter of the sky. The top plots aren't too important, but you might recognize something that looks a bit like the CMB wiggles in the plots at the bottom, and that's no coincidence. So this is the power spectrum of the galaxy over density fluctuations, basically. Here in configuration space is the correlation functions to the same thing. And the key observable from these data is the spacing of these wiggles or the position of this peak and the comparison back to what was predicted from the CMB. Okay, so I looked at what we could do with baryon acoustic oscillation data from galaxy surveys and other large-scale structure measurements alone without the CMB back starting in 2013. And if you don't use the CMB, so if you don't know the absolute length of the standard ruler of the sound horizon, then there's a perfect degeneracy between the sound horizon RD and H0. So in other words, you're looking at the same ladder if you're looking at different samples of galaxies at different redshifts, but if you don't know how long the ladder was in an absolute sense, then there's a free trade-off between the ruler length and the overall normalization of the expansion history, which is what H0 is. So we can get around this using extra information. So to provide a CMB independent input here, we can use estimates of the primordial deuterium abundance and knowledge of BBN physics to give us a constraint on the baryon density. And this is enough information to actually compute the sound horizon without using the CMB fluctuations. So no input from Planck. And this plot over here is showing that when you combine the BAO measurements from different redshift ranges, this is H0 against the fractional matter density in the universe. And the only region of parameter space that's allowed from combining all the BAO data we have from different large-scale structure surveys is down here at around 67 plus or minus 1 kilometer per second per megaparsec. And this is really, I wanted to emphasize the improvement in precision here, because in the 8 years since I first worked on this, the precision has come down, the uncertainties have come down by a factor of 3. So that's really testament to the improvements on the BAO measurement side. So this is a low value of H0 that's totally independent of Planck and an important part of the story. Okay, so just to sort of summarize H0 constraints from the early universe, I've put a set of values here. So all the blue points are from CMB experiments. The top set are measurements independent or made independently of Planck, the WMAP satellite, and then 2 ground-based experiments. The next set of blue points are different combinations within Planck, so splits in multipole. You can see that there's a mild preference of slightly different values here. Then there's this BAO plus deuterium constraint I was talking about, and finally the Shoes ladder for comparison. So there is some spread in the blue values. There's lots of these that have quite large error bars. Adding the BAO to the blue values has the effect of pulling you to a pretty small range of values centered around about 68. And you can see, each green bar is like a counterpart to the blue. So even though the original uncertainties are large in some of these experiments, the BAO are very effective at breaking the CMB degeneracies. And the message again is that even if you don't include Planck, BAO plus these other CMB experiments are giving values of H0 that are significantly low of the distance ladder. Okay, so just to summarize the early observations, by early, I mean sensitive to physics at or prior to recombination. There's some semantic confusion in the literature about this, but that's what I mean by early. So the CMB and BAO datasets are the key ones here, and they provide these precise but model-dependent predictions for H0, which are in tension with the distance ladder direct value. And so we're really left with two possibilities. Either the Shoes ladder is wrong, or our model is wrong. So the fact that we have both the BAO and the Planck-based constraints being precise and consistent and independent essentially rules out the possibility that the model is correct and the distance ladder is correct. So in the remaining few minutes here, I want to talk about what happens if we try and change the model. And I like this paper that discusses problems with this in more detail than I will by Ludlox and Marius Millier that I put at the bottom. So as you may know, there's $1 billion observational program underway to understand properties of dark energy. So I've just put up a few experiments here. In light of the Hubble tension, wouldn't it be wonderful if the Hubble tension was hinting that we didn't understand something about dark energy, and we have this next generation of experiments that are going to come in and really nail down what's going on and tell us something, fundamentally new about the universe. Unfortunately, modifications to the model that involve changing behavior of dark energy away from a cosmological constant, or more generally modifying late-time physics, are very tightly constrained by the data. So I love this plot on the left-hand side. This is combining CMB data with the BAO data, and also with a high redshift supernova sample. So not the supernova used to measure H0, but a sample covering a much wider range of redshift. And the blue constraint is H0 and the matter density in the standard lambda CDM model. And the red constraint is a model with 3 extra degrees of freedom. So the global curvature, whether the universe is open or closed, and then 2 parameters that control how the dark energy density evolves with time. So you add in those 3 extra degrees of freedom, and of course you make the contour fatter because there's more freedom in the model, but you really don't shift the value up very much. And this is the consistent story across all analyses, more or less all analyses that people have tried. And there are literally hundreds of papers that look at trying to modify the properties of dark energy to resolve the Hubble tension. I won't go through this plot in the right in detail, but it's essentially showing again that the low redshift measurements in conjunction with the CMB are extremely constraining on these models. Okay, so I wanted to put in a slide here about neutrinos. I apologize for compressing at least one talk's worth of material into one slide here. But as a cosmologist, I'm extremely excited about what cosmological observations currently and in the future can actually tell us about neutrinos. So here I'm just focusing on 2 things. Neutrino mass, first of all. So how do we constrain neutrino mass with cosmology? We basically use the property that the standard model neutrinos were relativistic at recombination, so when the CMB is emitted, but are non-relativistic today. And depending on the, more or less the sum of the neutrino masses, the sum of the mass states, that sets when that transition happened between now and when the CMB was emitted. And as far as we know, no other stuff in the universe has that property, right? Photons are always relativistic. Electrons were already non-relativistic back at recombination. And so that property can be used to basically get an indirect bound on neutrino mass, which is pretty precise. You can see that it's starting to put a bit of pressure on the inverted hierarchy. For the purposes of H0 and the H0 tension, unfortunately, allowing a wider range of neutrino mass in the fitting doesn't actually help. In fact, it makes things slightly worse. Because of parameter correlations in the model, higher neutrino mass actually leads to a lower H0 from the CMB side. So interesting, of course, that we can get these constraints, but not helpful for the Hubble tension. All right, another effect of neutrinos. So also from the CMB, primarily from the CMB, we can constrain the amount of the relativistic energy density at recombination that's not in the form of photons. So that could be standard model neutrinos, it could be other light species, stellar neutrinos. We can get a very powerful constraint on these, on what we call N effective, the effective number of relativistic species. And the main effect here is a change to the CMB damping tail, so how diffusion damping happens. So here we're showing a constraint, N effective against H naught, when this is added as a free parameter rather than fixed to the standard value. And it's true that there's a correlation with H naught, so that the prediction with H naught can trade off against changing the number of relativistic species. But the data are powerful. Planck plus BAO do not allow much of a deviation away from the lambda CDM values of H naught. So this is, again, something people have looked at as being an interesting prospect for resolving the Hubble tension. But in practice, it seems like this, extra relativistic species alone aren't really enough to get us there. Okay, and I want to highlight as well that I'm just talking here, or I'm not really talking about everything one could do in terms of neutrino physics and cosmology, of course. And there's a talk by Anna Bandas on self-interacting neutrinos and the Hubble tension, which I won't say any more about, but check out his talk. Okay, so wrapping up here, I wanted to discuss another idea that has received a lot of attention for trying to resolve the Hubble tension that I figured you might be interested in. So this is the idea of an early dark energy component. This plot on the left is from a paper by Katie Fries. This is showing density. So this isn't fluctuations, this is just background density against redshift. And we've got the normal components, so radiation in blue, matter in orange, and then a cosmological constant from what we think of as late time dark energy eventually coming in and dominating as the green. So early dark energy posits the existence of this extra fluid component that changes the expansion history prior to recombination. It doesn't interact electromagnetically, but if you're willing to accept arguably a bit of a contrived model, so there's some component that looks like dark energy here, and then it decays away, and it has to decay away at the right time and pretty quickly to not mess up the CMB power spectrum, but it does have the potential to modify that sound horizon I talked about before and change the value of H naught that we infer from the CMB. And there's been a series of papers written about this, and it's a similar story, I would say, to the case with modifying the properties of dark energy in the late universe. The issue is you end up messing up agreement with other measurements. So the plot on the right is showing the ratio of matter power spectra, essentially the clumpiness of matter on different physical scales. So the early dark energy models that achieve at least a little bit of an increase in H naught, nothing fantastic actually, but even in that case, an increase in H naught leads to this excess of power on small physical scales that actually exacerbates some of the tension between Planck and large-scale structure surveys. It's known as the S8 tension. And so, I think this is an interesting avenue for a bit more exploration. It's not clear quite how generic this problem is, this problem of worsening agreement with other data sets. Maybe there's some slight, different version of this early dark energy scenario that could do a better job. But right now, we're still a bit stuck, and we don't really have a great solution. All right. So to wrap things up, the H naught tensions persisted and worsened. I was checking the dates, and it's over 8 years since the initial Planck results came out. I've talked about the distance ladder, the CMB, and also the BAO as the key measurements in this. Although when it comes to testing models, a whole host of other cosmological data come in, and the real challenge here is that it's very difficult to increase the H naught prediction from Planck while still matching the other data sets that in lambda CDM are in pretty good agreement. Okay, and I'll emphasize once again that this is a huge sort of current hot topic in cosmology, and there's this big ongoing observational effort for independent constraints on H naught on the late universe side as well. All right, thank you very much, and I'm happy to answer questions.
Thank you, Graeme. I see a question here, so I will read it. Thank you for the nice talk. Do you have any comments on the very recent papers that might possibly remove the Hubble tension by using Cepheid color calibration, or questioning whether dark energy is an artifact? There are two papers linked on the chat.
Okay, probably best if I don't click on the links and look at the papers right now. I will check them in Slack, but I can give some answer to this. So there was a recent paper a few weeks ago that was called, it had a great title. It was like "The Hubble Tension Bites the Dust."
Yes.
And it was talking, that right. So it was talking, right, good. Okay, so I'm not an expert on what they're saying in that paper, but briefly, the idea is if you allow more freedom in the dust extinction to the galaxies hosting Cepheids and supernovae that are this middle rung of the distance ladder, then you can get different values of H0. That's the premise. So my understanding from talking to folks on the SHOES team, including Adam Rees, is that in principle, that's a valid test and a test that one should do. But in that paper, to get the low values of H0 sort of consistent with Planck, you have to do more than change the dust properties. Okay, you have to actually change the properties of essentially the color properties of the Cepheids themselves. And in that paper, they're allowing so much freedom that some of the Cepheids would never have been identified as Cepheids in the first place. So I think Adam's complaint basically is that there's too much freedom being allowed, and that if you made some cut such that you required the Cepheid properties to remain consistent with the selection of the Cepheids made by the SHOES team in the first place, you wouldn't have anywhere near enough freedom that they're suggesting. Obviously, that's a bit of a hand-wavy answer. I'm sure that the SHOES team are going to cover this in their next paper, which I think will be out pretty soon. But I think Adam is pretty strongly against that, the possibility that you could really change H0 by so much with that approach. I don't know about the other paper. I'll check it on Slack.
The other paper concerns is titled, "Do supernovae indicate an accelerating universe?"
Okay, well, the answer to that is yes. I think you have to, you have to do some weird things with supernova data or throw information out to not have the answer yes. But I'm not.
But if you have not read the paper, you cannot comment. Right. And I don't see other questions now. I have a very basic question that is: you mentioned these measurements on the new experiments which are being planned on the dark energy.
Sure.
Will be interesting, let's say, and you mentioned different models that can be tested in order to try and reconcile this discrepancy. Are there other examples in addition to the ones you have mentioned in your talk that you think?
Yeah. So I wanted to throw up a few kind of specific examples. I think generically you've got a sort of choice between modifying early universe physics, so early being again around recombination, so impacting the CMB, modifying late universe physics, which is more or less looking at dark energy. But there's a third category of models that I didn't mention, but I think is worth considering, especially because we've not gotten anywhere with the others, which is, going back to the fundamental assumptions about cosmology, looking at how gravity works, looking at, well, modifying gravity is probably the best motivated. So I think certainly experiments like Euclid are going to be potentially very powerful at constraining that aspect as well.
This is extremely interesting, in my opinion.
Yes.